Hello everyone, I'm Shuihai Hu from Class Star in the HKUST. Today, I would like to talk about our work, Aeolus, which proposes a new building block to augment proactive transports in data center networks. As you may know, in recent years, as shown in the figure, the link speed of production data center networks grows very fast, from 1G to 10G to 100G, with 200G on the horizons. Given this trend, congestion control in data center networks has become much more challenging. With link speed increased by 10 to 100 times. Today's data center networks have much higher bandwidth delay product and more burstiness, and the flows now finish in much fewer RTTs, leaving the transport very little time to react to congestion. Today's congestion control are mainly achieved using reactive protocols. Reactive solutions, such as TCP and DCTCP, react only after congestion already happens. Reactive solutions have long-standing problems, including switch queue buildups, severe loss on the incast, and very slow convergence speed. With higher link speed, all these problems now become worse. Proactive congestion control solutions, or PCC, have drawn great attention in recent years. Compared with reactive solutions, proactive solutions have several advantages, including near zero queuing, zero packet loss, and fast convergence. Unlike reactive solutions, the key idea of PCC is to proactively schedule network transfer based on the availability of network resources using credit. The idea of PCC can be realized in several ways. For example, FastPass employs a centralized arbiter to enforce a tight control over network transfers. PDQ and TFC leverage switches to explicitly allocate link bandwidth among all passing flows. ExpressPass, NDP, and Homer use receiver-driven, credit-based approaches to explicitly schedule the arrival of data packets destined for different receivers. While being promising, all existing PC solutions require one HRTT to prepare the schedule. In high-speed networks, we find that the cost of delaying all flows by one HRTT can be very expensive. Our observation is that at a high link speed, a large portion of flows could complete in the first RTT. In this figure, we show the fraction of flows could have been finished within the first RTT under different link speeds. Although our measurement methodology is idealized, the results suggest a very clear trend that the rise of high-speed data center networks makes the first RTT much more important. As we can see, at 100 Gbps, 30 to 80% of flows could have been finished within the first RTT. However, existing solutions cannot well handle the one HRTT problem. They mainly fall in two categories. One line of work should to pay the cost of one extra RTT. For example, in ExpressPass, the sender will send a credit request to the receiver on the arrival of a new flow. On receiving credit request, the receiver will send credits to the sender. The sender will then send data after it receives credit. So it's easy to see that all flows are delayed by at least one RTT on the express path. At a high speed, the cost of wasting first RTT can be very expensive. To demonstrate this, we measure the flow computing times of 0 to 100 kilobytes flows with 100G bps link speed. Flows are generated according to cache follow workload. As we can see, compared with idealized solution, 80% of small flows take 1 HRTT to complete when on the express path. A second line of work that new flows blindly send traffic in the first RTT, such that the 1 HRTT can be removed. For example, in Homer, on the arrival of new flows, the sender will send a BDP of unscheduled data packets. However, these unscheduled packets sent in the first RTT may cause large queue buildups and severe packet loss. As a result, good properties of PCC are violated. To demonstrate this problem, we study the flow performance of 0 to 100 kilobytes small flows on the Homer and the idealized solution. Flows are also generated according to the cache follow workload. As we can see, compared with idealized solution, the tail FCT on the Homer is extremely long. This is because some scheduled packets get lost due to buffer overflow and trigger flow timeout. The results indicate that blind burst can cause serious performance downgrade. To this end, it's natural to ask such a question. Can we eliminate the 1 RTTH delay while preserving all the good properties of PCC? Our answer to this question is Aeolus. Now we talk about the design of Aeolus. This is a design overview. As we can see, Aeolus mainly contains 3 components: rate control, selective dropping, and loss recovery. Aeolus adopts a minimal rate control at the end host. All flows start at a line rate in the first RTT. This can maximize the chance for new flows to utilize the spare bandwidth. In a network, to safeguard scheduled packets and preserve all the good properties of PCC, Aeolus introduces a novel selective dropping mechanism at the switch. This mechanism will selectively drop unscheduled packets when spare bandwidth is used up. So scheduled packets will not be affected by unscheduled packets. We will introduce more details about the selective dropping mechanism later. Given Aeolus has safeguarded the scheduled packets, loss recovery is needed only for unscheduled packets. In our design, we leverage the well-protected PCC as a safe and efficient means for recovering lost unscheduled packets. In the next, I will introduce the selective dropping mechanism in details. At the end host, this mechanism performs packet tagging. Unscheduled and scheduled packets will be tagged with different tags. In a network, switches perform selective dropping to protect scheduled packets over unscheduled packets. So, what is selective dropping? As we can see, selective dropping is a switch buffer management scheme. It configures a dropping threshold at the switch egress queues. When queue occupancy reaches the preset dropping threshold, the incoming packets carrying low priority tag will get dropped, In contrast, packets carrying high priority tag will still enter the queue and get served. Now, let's see why selective dropping works. When network is underutilized, unscheduled packets will enter switch queues. As a result, spare bandwidth is utilized and there is no 1 RTTH delay. When network is fully utilized, unscheduled packets are selectively dropped. As a result, scheduled packets are not affected, and all the good properties of PTC, including low latency, zero packet loss, and fast convergence, are well preserved. While the selective dropping mechanism is appealing, the key question is how to implement it with existing commodity switches. We leverage ECN, a built-in function of commodity switches, for the implementation. So, what is ECN? ECN is a switch mechanism which allows switch to perform congestion notification by marking a specific field in the IP header. In the IP header, there is a 2-bit field called the ECN field. ECN field has 4 code points in total. 00 means a flow is not ECN capable. 01 or 10 means a flow is ECN capable. 11 indicates a flow has encountered congestion in the network. In our past test-bed experiments with ECN, we made an interesting observation. Let's assume the queue occupancy already reaches the ECN marking threshold. Our finding is that if a packet is ECN capable, it will enter the queue and get ECN marked. But if a packet is not ECN capable, it will be dropped by the switch. Based on this observation, we can implement the selective dropping mechanism by reinterpreting the ECN marking function. At the end host, we tag scheduled packets as ECN capable and unscheduled packets as ECN incapable. At the switch, we simply set the ECN marking threshold equal to the selective dropping threshold we want to configure. With these simple configurations, we can implement the selective dropping mechanism using existing commodity switches. Priority queuing is an alternative solution to selective dropping mechanism, as shown in the figure. By having scheduled packets enter high priority queue and unscheduled packets enter low priority queue, we can also ensure unscheduled packets only utilize the spare bandwidth for the first RTT transfer. However, priority queuing have 2 drawbacks. First, it will require 1 additional queue for each service class, such that the number of supported service classes will be reduced by half. Second, due to the queuing delay in the low priority queue, there can be packet reordering problem. This can be illustrated with a simple example, as shown in the figure. A sender sends 3 unscheduled packets and 3 scheduled packets. In a network, scheduled packets are served with high priority queue. As a result, scheduled packets with a larger sequence number arrive prior to the unscheduled packets, leading to packet reordering problem. With the selective dropping mechanism, scheduled packets are well protected from congestion loss. However, unscheduled packets could still suffer from congestion loss under heavy load. To handle this, we designed a faster recovery scheme for unscheduled packets. The first step is to detect loss quickly. To do that, we enable per packet act for each unscheduled packet. In addition, we also design a tail loss probing mechanism for quickly detecting tail loss of unscheduled packets. The second step is to retransmit lost unscheduled packet quickly. Our idea is to reuse preserved PCC to guarantee retransmission. This is done by retransmitting lost unscheduled packets only with scheduled packets. This is the evaluation setup. For our test-bed evaluation, we implement an Aeolus prototype with DPTK. We built a small testbed using 8 servers connected to one mellanox 10G switch. As for our simulations, we conduct experiments using 3 simulators, including NS2, ONET++, and HTC. We use a 100G multi-tier span-leaf data center network topologies and generate flows according to realistic production workload. First, we evaluate whether Aeolus can assist express paths to remove the 1 RTT extra delay without hurting the good properties of PTC. These 3 figures show the flow completion times of 0 to 100 KB small flows across 3 workloads, including web server, cache follower, and web search. As we can see, with Aeolus, a large portion of small flows complete within the first RTT. The results indicate that Aeolus can assist express paths to significantly speed up small flows by removing the 1 RTT extra delay. Second, we evaluate how Aeolus can assist Homer to preserve the good properties of PC without putting new flows in the first RTT. These 3 figures show the FCTs of small flows under Homer with and without Aeolus across 3 different workloads. As we can see, without Aeolus, flows suffer from very large tail FCT due to packet loss caused by first RTT burst. But with Aeolus, there is no packet loss, and the tail FCT is reduced from more than 100 milliseconds to be less than 800 microseconds. This indicates that Aeolus can assist Homer to eliminate large queues and the loss of scheduled packets, thus significantly improve the tail FCTs. We also evaluate whether Aeolus can assist NDP to achieve similar performance without the support from expensive customized switches. The 2 figures on the left show the FCT of small flows on the NDP with and without Aeolus across 2 workloads. The 2 figures on the right show the average and the maximum queue length on the both schemes using web server workload. As we can see, regarding all the measured metrics, both schemes achieve very similar performance. The results indicate that Aeolus can assist NDP to achieve similar performance without the supporting of expensive customized switches. Now, let me do a brief recap of Aeolus. Aeolus is motivated by the problem that proactive transport requires 1 HRTT for scheduling packet transmission. To solve this problem, we designed Aeolus, a simple and general building block for augmenting all existing PCC solutions. With Aeolus, 3 important goals are achieved, including eliminate 1 RTT extra delay for new flows, preserve all the good properties of PCC, and work with commodity switch hardware. This is the end of my talk, and thank you so much for your attention.